Well, hello and welcome YouTube. Mr. Robinson back here with yet another brand new exciting video, all math-based of course. And as always, it is an honor and a privilege to be serving here today as it is every day here in my virtual classroom. Step on inside. We are continuing our geometry stuff. Now looking within triangles, perpendicular and angle bisectors. That is perpendicular bisectors and angle bisectors. I guess within, well, not necessarily within triangles, but you'll see the formation of triangles sort of appear within. This chapter is on triangles, you see, and everything that we've talked about so far involving proofs, things with perpendicular lines, and I forget all the proofs we did last time. Vertical angles, talked about corresponding alternate interior, all that's going to exist within the triangle stuff we do, I imagine, or at least it's a part of geometry. It's the intro stuff we've done from IM1. This one's a little more IM2 this time. This one's a little more, you might not have seen it before. You might have heard of these, but now we're using theorems within them and how they're used in these processes. So we'll take a look at them, perpendicular and angle bisectors. I'm going to get started on it. I'm very curious as to see how they go about certain things. Obviously, I'm sight reading it as we go. Core vocabulary, we got to know the word equidistant. Equidistant means two things that are equal distance. Or not necessarily two things, a multitude of things. And perpendicular bisector, angle bisector are the key words. Obviously, they're going to define them for you, but we'll talk about them. You are going to use perpendicular bisectors to find measures. And this is a common thing. They'll either have just a number, a constant value, or something in an algebraic equation, a very basic one for you to solve. Use angle bisectors to find measures and distance relationships. We'll see what they mean by the distance relationships part. And write equations for perpendicular bisectors. That might be a word problem-based thing. I'm actually not sure. Okay, using perpendicular bisectors. So we must have learned this. Maybe it was part of our proofs. I honestly don't remember. Previously, you learned that a perpendicular bisector of a line segment is the line that is perpendicular to the segment at its midpoint. So what they're saying is, if one line's perpendicular to another, that's what makes another line, that's what makes the right angle. If a line's a bisector of a segment, then it's dividing the segment into two congruent parts. So if a line's a perpendicular bisector of a segment, it's intersecting it at 90 degrees and it's dividing it into two congruent parts. Note that a line can't be bisected, but it can be a bisector. One is bisecting the other. You got to make sure you know which one is which. Now, a point is equidistant from two figures when the point is the same distance from each figure. That is that definition. Same distance, equal distance. You're going to hear a theorem where they talk about that. Okay. The perpendicular bisector theorem states, in a plane, like on this screen, if a point lies on the perpendicular bisector of a segment, such as C, is on the perpendicular bisector, then it is equidistant from the endpoints of the segment. This distance and this distance are the same. The length AC is equal to the length BC. That's the statement that they're making. So any point that's on this line, as long as this line is the perpendicular bisector of the segment, those points are equidistant. You might understand the logic behind that, but it is a theorem. It can be proved, and we're probably going to have to dive into the proof, either in the assignment or in this example, in the notes. So if CP is perpendicular bisector of AB, then CA equals CB. Keep in mind, these might not be actual segments. These are just distances, and I think that's an important concept to note. This might not be a physical side of a triangle. I mean, clearly it looks like we're talking about an isosceles triangle right now, but that blue is more of an abstract thought. They are talking about distances, not necessarily actual side things. They could be, though. Just keep that in mind. Oh, there's a proof on page 344, whatever. I don't know what page I'm on, so. Now, the converse of the theorem states kind of the opposite effect. So in a plane, if a point is equidistant from the endpoints of a segment, then it lies on the perpendicular bisector of that segment. Now, not all segments have perpendicular bisectors, but if someone said draw the perpendicular bisector, that means that a point D, being equidistant to both A and B, must be on that line that you could draw that would go through as a perpendicular bisector. So that's what it means. So the converse also works, which just, this works both directions, which is very cool and very nice. Now we're going to be able to use those things here. All right, this is page 344. So here is that proof that they're referring to. They have a paragraph proof version of it. I wonder if they have a 2-column proof. So I'll try and walk through the paragraph proof with you guys and see what they say. Because CP is the perpendicular bisector of segment AB, I mean, this is going to be a triangle proof thing, just so you know. Perpendicular bisector of segment AB. Line CP is perpendicular to segment AB. There's the perpendicularity. And point P is the midpoint of AB. By definition of midpoint, these two lengths are equal, and that would then make those segments congruent. Definition of segment congruence means those are congruent. Boom, there's the marking. And by definition of perpendicular lines, these two angles are congruent. They're both 90 degrees, and they're both congruent. By the reflexive property, oh wait, hold on, CPA and CPB. So these two angles are congruent. They're spelling everything out very largely. By the reflexive property of congruence, segment CP is congruent to itself. So now we have this triangle here, triangle CPA can be congruent to triangle CPB by the side angle side congruence theorem. Boom, 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 boom. And therefore, CA, segment CA, would be congruent to segment CB if these were indeed triangles by CPCTC. If the two triangles are congruent, then the corresponding parts are congruent. And that is the proof. So if you know about triangle congruence, you know what I mentioned, and I wanted to walk through it because we talked about proofs recently. Okay, let's use the perpendicular bisector theorem to find each measure. They ask us to find the length of RS, segment RS here. From the figure, SQ is the perpendicular bisector of PR. You have the symbol of perpendicularity. You have this congruent, which means Q is the midpoint, which means it's bisecting it. So they want to find the length of segment RS. We know that a perpendicular bisector, any point on the perpendicular bisector, I should say, is equidistant from the endpoints of the segment. That means if this length is 6.8, then this length is also 6.8, which is what they say. That's part A. Part B example, find the length of EG. Well, in here, I mean, they're explaining it, but they do have a perpendicular line here. They do not state whether or not it's a bisector. They just state it's a perpendicular line. But they do show that these are both 24, which means if this point is equidistant to the endpoints of the segment, then that means that it is on the perpendicular bisector of that segment. And we know it's on the perpendicular portion for sure. So that means that F is the midpoint of this segment, which makes this thing 9.5. But they say find the length of all of EG. If this is 9.5 and that's 9.5, you can double it up and you get 19. Third example, find the length of segment AD right here. Once again, you have a perpendicular bisector, but this time it's set up algebraically. So although these are congruent, they have equal lengths. Length of AD is length of CD. We set them equal to each other to then solve for X. Now, solving for X, 7, allows you to find the length of segment AD by substituting that 7 in for X. Now, you could substitute it into here, which you probably would, 5 times 7, but you could also technically plug it into here. 3 times 7 is 21, plus 14 is 35. They should both get you 35 because they're equidistant. So, there you go. All right, so that is and by the way, I don't know if I mentioned this or not, but part B, we're using the converse of the perpendicular bisector theorem, noting that this is indeed a bisector, perpendicular bisector, because it was equidistant. Both of these were the actual theorem, A and C. Okay, solving a real-life problem. Is there enough information in the diagram, good question, to conclude that point N lies on the perpendicular bisector of segment KM? So we got a diagram over here. Here's point N, and we have KM. So I guess we have to look at the diagram itself. It's an example, so it's written, but there's congruent tick marks here and here. I don't see a perpendicular, symbol right here. I don't see something that looks like that. So I can't say whether it's perpendicular bisector. Can we conclude it lies on it? There's nothing else that says that these parts are congruent either. So let's see what they say. I say no. It is given that those two segments are congruent, KL and ML, so it's a segment bisector, but you do not know whether it's perpendicular, so you cannot conclude it. Now, if they showed these were congruent, sorry if you can't see that, if they showed those were congruent, I could conclude it. It's not enough. You cannot conclude that it lies in there. Okay, some monitoring progress stuff for us to do for our own problem set, so I'll leave that be. Okay, angle bisectors, let's talk about those. Now, I don't know when we learned. See, I can't remember if we talked about these in section 6.1, so I really apologize. Maybe it was part of IM1 stuff. But an angle bisector is a ray that divides an angle into two congruent adjacent angles. So this angle here is congruent to this one because ray AD is a bisector of angle BAC. That's kind of what they're bringing up here. Those two parts are congruent. It goes right down the middle. You also know the distance from a point to a line is the length of the perpendicular segment from the point to the line. What they're saying is, I want, if D is a point, I want the distance from D to this line right here, to this AB line right here. How do we calculate a distance if there's an infinite number of points on a line? Technically, the distance we're supposed to be measuring is the shortest distance. And what's the shortest distance? It's always the perpendicular distance. That's what they're bringing up. This distance from here to here is the perpendicular. See, this isn't perpendicular, but that's longer, and that's longer, and that's longer, and that's longer. So the shortest distance is always the perpendicular distance. That's what they're mentioning. So why are they bringing those two things up? Well, the angle bisector theorem. The angle bisector theorem states the following. If a point lies on the bisector of an angle, such as point D, D lies on the angle bisector, then it is equidistant from the two sides of the angle. So D's distance to ray, ray AB, is the same distance, boom, as D's distance to ray AC. Here, boom, it's two congruent marks, like that. Boom, boom, they're the same distance, that perpendicular distance there, because it's on the angle bisector. It's on the bisector of the angle, right there. That's the theorem. There's a proof somewhere, I'm sure. If not, it's a congruent triangle proof. I think already I could give you HL, that this right triangle here is congruent to that right triangle, therefore by CPC. Oh, I'm sorry, we actually wouldn't know that's congruent. Excuse me, this would be angle, angle, side. Angle, angle, side, angle, angle, side would prove it, therefore by CPCTC. It is there. Shows a proof on page 350 as well. I'm sure we're going to be able to look at it, maybe. Maybe it's part of the problem set. I didn't even think about that. Okay, the converse of the theorem is also true if you switch everything around. If a point is in the interior of an angle such as D, you don't know anything else about the bisector bit, and it's equidistant from the two sides, if you're given that it's the same distance away, remember the perpendicular distance, then that means it lies on the bisector. So that means these are therefore congruent in that stuff. It is on the bisector there. Once again, it can be proved. That's the whole point of theorems. So it's also true. Let's use these in examples that are pre-written out. Find each measure, the measure of angle GFJ, right there. We want to find that. Well, we know that point J is equidistant from ray FG and ray FH. Being equidistant means J lies on the angle bisector. That means these two angles here are congruent. So if this angle measure is 42 degrees, then this angle measure must also be 42 degrees, which is what they're asking for. Measure of angle GFJ is 42 degrees. Part B, the length of segment RS. Length of segment RS right here. We are given that there's an angle bisector here, QS, because of the congruent angles. Therefore, these two segments are, point S is equidistant from those two sides of the angle. So these two segments are congruent, you should say. So these two lengths being equal, you can set them equal to each other and solve for X. In doing so, we can find the length of segment RS, or this distance, by substituting that answer 5 in there to get 25. Some more monitoring progress, things we're going to do in a bit. Probably the last page of the notes bit, solving a real-life problem. A soccer's goalie position relative to the ball and goalposts forms congruent angles at a single moment in time, as shown. Will the goalie have to move farther to block a shot towards the right goalpost or the left goalpost? So a soccer's goalie position relative to the ball goalpost form congruent angles as shown. So it's not really marked well, but I sort of see a thing there and there. Those are congruent. They're asking, will they have to move further to the right and left? Well, if the goalie is on the angle bisector, right? If the goalie's point is on the bisector itself, then it should have to move the same distance to the left as to the right. The congruent angles tell you the goalie is on the bisector. By the angle bisector theorem, it's equidistant from both things. The goalie must move the same distance to block either shot. That way and that way are the same amount. Okay. Writing an equation for a bisector. Oh, interesting. Okay, we get to kind of use some algebra things within here. I mean, in full. So get ready, get your algebra hat on for this one. Write an equation of the perpendicular bisector of the segment with endpoints P of -2, 3 and Q at 4, 1. Looks like they're going to use slope-intercept form, so I'll follow suit. I am more familiar, I would normally advise point-slope form for this, but slope-intercept form is great. Okay, so here is this line, not M, this line y equals 3x minus 1 right here. What you want to do, well, how are they talking about it? Write an equation of the perpendicular bisector. Why are they asking for a midpoint? I don't know why they're asking for the midpoint. Oh, they need the bisector. I was thinking they needed this line for PQ. Got it. Okay, this is the answer apparently. Okay, I missed that. My bad. Here's the original segment. We need the equation of the red line. Got it. Okay, so they need the midpoint here because they need to know where it's going to cross through. I would still be using point slope form if I had a choice. Okay, so we find the midpoint first. How do you find it? You average your x values of P and Q, and you average your y values of P and Q. P's x value is -2, Q's x value is 4. The average of those, add them up and divide by 2, and you get 1. So the midpoint x value is 1. The y value, you average the heights of 1 and 3, and you get 2 in the middle there. So 3 plus 1 divided by 2 is 2. So midpoint of 1, 2. That's important because given that, we're going to be able to figure out what the, just basically where the line goes from there. It's a reference point that we can use. There's nothing else. Remember, you don't have this line. It's not technically there unless they draw it for you and thing, in which case they're being a really good sport for that. Now they find the slope of PQ. How come they do that? Because the perpendicular slope is going to be what's called the opposite reciprocal of this one. So you can see that this is a slope of, from P to Q, you go down 2 over 6, or you could say you go down 1 over 3 if you have the midpoint, or any other count that you want to do, but -2 over 6 also reduces to -1/3. Now the opposite reciprocal, they call it a negative reciprocal, the opposite reciprocal of -1/3, you change the sign and you flip the fraction, so it becomes +3. So that means this slope of that line, which you can see is up 3 over 1. Now, when it comes to writing an equation, write it in slope-intercept form, that's where that 3 comes from, that's the slope. How do you get the y-intercept of -1? You could kind of draw it out and work off that, but they use more of a mathematical formality. They use slope-intercept form, y equals mx plus b. They substitute the x value of the midpoint, they have 1, the y value of the midpoint, they have 2, into this equation to find their b. M is their slope, 3 times 1 is 3, subtract 3 from both sides, you get a b value of -1. So if your m is 3 and b is -1, your final equation in slope-intercept form is y equals 3x minus 1. That's the equation that would be the perpendicular bisector of segment PQ. It cuts through the middle, and it goes at a right angle. Okay. Now, these are things that, I don't know, you probably learned a little bit in IM1, but they're kind of bringing it back. Okay, that seems to be the end of that part, and probably, yes, the end of the notes bit there. Let's start looking at vocabulary and core concept check before we do the actual problem set. Complete the sentence. Point C is in the interior of angle DEF. If angle DEC and angle CEF are congruent, then ray EC is the blank of angle DEF. Without them trying to trick you, we could draw it out as well. Here is, say, angle DEF, and point C is in the interior, like here, like that. If these angles are congruent, angle DEC and angle CEF, then ray EC is known as the angle bisector of that. That doesn't have anything to do with the angle bisector theorem, the one that states that these points are equidistant here and here. That just states that's how angle bisector, that's what an angle bisector is. So there's that. Okay, different word, same question. Which is different? Find both answers. All right, you can see that this B, and there's no other letter here. Let's just make one up. Let's call it Y. That segment BY is the perpendicular bisector of segment XZ. So we also would know that if there's no segment drawn here, but I can kind of just draw dotted distances to give an abstract thought. That would also mean that these two distances are congruent, right? They're equidistant. B is equidistant to X and Z. Is point B the same distance from both X and Z? So let's say that that's a statement A. Is point B equidistant from X and Z? That's the same thing. Point B the same distance, equidistant, boom. Is point B collinear with X and Z? That's a different question. That would be like Y. This point Y is collinear with X and Z. You can draw a straight line through those ones. This is a different question than those two. Is point B on the perpendicular bisector of segment XZ? You betcha. That one definitely is. So all three questions here, A, and A, are all true to this statement and will always be true for statements of perpendicular bisectors. Point on the perpendicular bisector is equidistant or the same distance away from those. Collinearity has to do with what Y is doing. So that's the different one there. Okay, guys, that is the end of everything before the official problem set that I'm going to do with you guys. So go and check out the PDF down below in the description section. Download that thing and let's be rocking and rolling together, shall we? We got numbers, I think it's 3 to 38. I'm going to pop that up right now and see what we got. Yes, sir, numbers 3 to 38. Let's get going and let's start ourselves off with numbers 3 to 6, where we find the indicated measure and explain our reasoning. This might be a set where I do a lot of copying and pasting, so please bear with me. I did not foresee that thing. You know what? I don't really know if I have to. I don't know if I have to copy and paste that. See if you can go along with me. See if it'll make enough sense that I do it without it. You can look at the diagram, right? And I can point to it. So they need to find the length of GH. You can see here that HK, line HK, is perpendicular to line GJ. And because these are both 3.6, that means they're equal lengths. That means those are congruent, which means that K is the midpoint of GJ. Another way of saying HK is the perpendicular bisector of GJ. If that's the case, then that means these two segments should be congruent. If HJ is 4.6, then GH is also 4.6. The length of GH equals 4.6. It says explain your reasoning. I don't know if they mean the perpendicular bisector theorem, whatever. I said everything out loud, so that's what I'm going by. So go by what I'm saying. That's going to be my reasoning there. Hope that that's okay. I'll explain it in full. Number 4, the length of segment QR. Here you have point T, and line TR is the perpendicular, perpendicular to segment QS, but point T, being on that perpendicular portion, it's also equidistant to point Q and point S, the endpoints of that segment. This is the converse of the perpendicular bisector theorem, which states if T is equidistant to those 2 points, then it is on the perpendicular bisector of that segment. So, because this is the perpendicular part, you know that R is the midpoint of segment QS, and if RS is 1.3, then QR is also 1.3. That is number 4. That's the converse of the perpendicular bisector theorem. That's what I'll put for these things here. I'll put perpendicular bisector theorem. I don't know if that's what they mean as reasoning. And converse of perpendicular bisector theorem. A lot of abbreviations here. Number 5, the length of segment AB. So, line DB here shows perpendicularity, which means B could be the midpoint. If we get more information, there's not enough yet. But take a look. D is equidistant to points A and C, the endpoints of that segment there. Therefore, DB also represents the perpendicular bisector of segment AC. That means these two guys are congruent here. So we need to find the length of AB. In order to do that, we have to solve for X. We are going to set the length of AB, 5X, equal to the length of segment BC, 4X plus 3. Let's solve for X by subtracting 4X from both sides. You get X equals 3. See, it's going to be very basic algebra that you do. That's not the answer, by the way. X equals 3. So the length of segment AB, therefore, we're going to substitute 3 for X, 5 times 3, and you get 15. There are no units presented here, so I can't really say inches or anything like that. It's 15 units. We're just going to leave it as that. Oh, that is the this is the converse of the perpendicular bisector theorem. Okay, number 6. The length of segment UW. Don't let the diagram trick you more than, it would need to or not, what have you. But the length segment UW, you can see that this line UX, or UD or whatever. It's the perpendicular bisector of segment VW. It shows the perpendicular symbol and the segments that show the D is the midpoint of that. Therefore, U is equidistant to points V and W. That means that this segment is congruent to this segment, which means we can set those lengths equal to each other, which is exactly what we're going to do. We get 9x plus 1 equals 7x plus 13. We're going to solve for x to begin with. Subtract 7x from both sides, we get 2x. Subtract 1 from both sides, I get 12. Divide both sides by 2, you get x equals 6. They need to find the length of UW. UW is this guy right there, represented as 7x plus 13. Note, I could plug 6 into this one as well. I should get the same length. It doesn't matter because they are equidistant. But we're going to do it in the one that's representing it. I think that's most fair. So 7 times 6 plus 13, that's 42 plus 13, or one of my favorite answers, 55 for number 6. Okay? Let's move forward to numbers 7 through 10. Tell whether the information in the diagram allows you to conclude that point P lies on the perpendicular bisector. Oh, let me state here, by the way, this is the perpendicular bisector theorem. That lies on the perpendicular bisector of segment LM. Explain your reasoning. Not always a fan of explaining my reasoning, sorry, but I'll do what I can. Number 7. Do we have enough information to conclude that point P lies on the bisector itself? Well, here you have NK or NP, however you want to say this, ray. This is perpendicular to that segment. It doesn't show that it's a bisector right there, right? We don't show those parts, but we could show those parts because N is equidistant to points L and M, the endpoints of the segment. Therefore, yes, P also on that perpendicular ray is therefore on the perpendicular bisector of segment LM. Yes. So for number 7, here's what I'm going to write. I'm going to type it. Because N is equidistant from L and M, the endpoints of the segment that is, I don't know, intersected, perpendicularly intersected with. And P is on the ray that is perpendicular to that segment. I'm probably overwording this. Then P is on the perpendicular bisector of that segment. Yeah, that's a lot for you guys to end up writing as well, but they said explain. And explain I shall. All right, number 8. P. We're looking at point P here, right? So we hear this. So this time we know there's a perpendicularity right there. And it shows a different congruency, though. This segment PN is congruent to segment NL. But PN being that potential perpendicular bisector, it's perpendicular to it. I don't care that this is congruent. It can be congruent all at once. What I need to know is whether this part's congruent right here, you know? I need to know this. And I have no knowledge of this bit of information. For all we know, this could be extending like this. Remember, nothing's truly drawn to scale, meaning it's open to interpretation, unless it is mentioned or marked in a certain way. So it's not open to interpretation that these two segments are congruent. I can't redraw their configuration. You got to assume those are equal in size and shape. This one, I don't know. This could be extending out. Therefore, P is perpendicular to that segment, but I don't know if it's on the bisector. I don't know that's congruent. There's no way, not through Pythagorean theorem, any way to determine that it is. So no, there's no way you can conclude it on that one. Although P is on the perpendicular segment to the segment in question, there is not enough information to conclude that segment LN, or the length segment LN, is equal to the length of segment MN. In any way, not even using the converse or anything, right? There's nothing that says that. Therefore, there's not enough information to conclude that P is on the perpendicular bisector. think I've already committed to how I'm typing it, but next time I'll say no or yes, and then I'll explain, so I don't have to do the therefore thing at the end. I think that probably makes more sense. I'm cooking myself out with this heater. I might turn off my heater here in a moment. All right, number 9. Okay, so number 9 almost appears different in that, so you know this thing that I was saying here, we're like, oh, I don't care that this thing is this or whatever. Well, as long as those are congruent there, that helps. That means that n is bisecting that thing. The question becomes whether it's perpendicular to it. And I don't feel the information's there. Here, I mean, listen, what you want to learn to do as a geometrist, I don't know, here. I'm going to draw it on this other side. What you want to learn to do is draw exceptions to what they're constructing. So, for example, let's say I did something like this. Okay, I'm going to make these all congruent like that. Okay, so I think it looks close enough that like this is congruent to that is congruent to that. Maybe it's off by a little bit, but those are all congruent. But notice how I slanted this, and then how this can also, I'm going to extend this outward now. But notice how I slanted that thing. I'm going to reconstruct this drawing, but with a different take on it. And it looks like this now instead. Notice that it's completely not perpendicular, right? We don't have information about maybe these being the same, right? These are clearly not the same anymore. Those are different, right? Those are different looks. There's not enough information, even by those being congruent, that it's on the perpendicular bisector, because we don't know anything about these segment lengths here being the same or not. We don't know anything about that being perpendicular or not. So, no, there's not enough information here. It's on a bisector. It doesn't matter that that other part is congruent. It's great that it is, but it doesn't matter. It's not necessarily the perpendicular bisector. So number 9, although P is on the bisector, there is not enough information to conclude that it is perpendicular. So what you have to remember is what I drew, and that's all I'm going to say. So what I drew, keep in mind, is showing the exception to that, right? A counterexample that shows that thing false. You cannot look at this drawing and say it looks perpendicular. That's not the point, right? We have to provide counterexamples to the information that we have. And that's the important part about geometry that a lot of students do struggle with. And that's where maybe they understand that concept, but they have trouble finding a counterexample. But it's all about finding those and say, can I do something that would offset that rule? Now, I wouldn't try and disprove a theorem. If a theorem is proven itself true, don't try and disprove it. You're not going to do it. But, you know, just like so, the perpendicular bisector theorem, don't try and offset it. It won't work. It won't break. Okay, so this next one here, looking pretty good. There's equidistance right here to these two things. That means that this point P being equidistant, that means that as long as it's drawing through the part that is bisecting this, that means this would also have to then therefore be perpendicular. See, it's not enough to just know, and I can't really hide these, let's just say that they're gone. It's not enough to just know that P is equidistant to those things. It's great if it is. It means it's on the perpendicular bisector, but does that mean that we drew a perpendicular bisector, right? That this thing's drawn as one. And we don't know here, but we do know here because we have the bisector information. Therefore, this also must be perpendicular. So yes, it's on the perpendicular bisector, and that perpendicular bisector is drawn. Because P is equidistant to L and M, P is shown to be and N is the midpoint of segment LM, then it is shown that P is on the perpendicular bisector of LM. Like, it's drawn as such as well, which is nice. Okay. That's those ones. Hopefully those explanations made sense. Hopefully I got to walk through it with you a little bit. Okay, numbers 11 through 14. Let's find the indicated measure and explain your reasoning. Now we're talking about angle bisectors. So in the first drawing, or the angle bisector theorem at least, because in the first drawing, I don't necessarily see an angle bisector here. By the way, the 20 degrees they're talking about is this arc right there, that angle. So this angle, this measure is 20 degrees. They want to find the measure of angle ABD. This is the one in question right here. In question. But we have some information. We have this point D from this ray, BD, and D is equidistant to ray BC and ray BA, which is part of the angle bisector theorem. It states that a point equidistant to the sides of an angle is on the angle is on that angle's bisector. Therefore, that makes these two angles in here congruent. So if the measure of angle CBD is 20 degrees, then the measure of angle ABD is also 20 degrees. They say explain your reasoning. This is the converse of the angle bisector theorem. Whoops. You know what I should be putting? I should be putting this. It equals the measure of angle CBD equals 20 degrees. I'm kind of just bringing up that knowledge that this is what we're actually looking into. So that is the converse of the angle bisector theorem. You might be curious, Mr. Robinson, how do you remember which one is the original theorem, which one's the converse? The original theorem starts with if it's a perpendicular bisector, then, or if it's an angle bisector, then. The converse states is the converse is, state if something something, then it is a perpendicular bisector, or then it is an angle bisector. So the original theorems start with the condition being that it is a perpendicular bisector of some sort, whatever. That's what we're going with. So this is the converse because we determine it is an angle bisector because of the information we have. All right, number 12, the length of segment PS. You can see that ray QS happens to be a perpendicular bisector of angle PQR because these two congruent angle marks there. Therefore, S is equidistant to the two sides of the angle here, meeting at points P and R, the perpendicular distances. So if the length of SR is 12, then the length of PS is also 12. So PS is the length of RS, which is 12. That is the angle bisector theorem. I'm just going to put the angle symbol. Angle bisector theorem. That's the reason that I'm providing. That's my explanation. Number 13, measure of angle KJL. And you see the 7x degrees. Once again, we're referring to this guy, and then they point to this guy being the 3x plus 16 degrees. Now, are those two congruent? Well, yeah, you betcha. You have, once again, L being equidistant to points M and K, points on the sides, perpendicularly, points on the sides of the angle, here, KJM. Therefore, by the converse of the angle bisector theorem, JL is the angle bisector of the angle, which makes these two parts congruent, which makes these measures equal. I can write that 7x equals 3x plus 16. I can solve for x, subtract 3x from both sides, and divide both sides by 4, like so. But they do want to find the measure of angle KJL. You can see it marked as 7x degrees. So we're going to say the measure of angle KJL is 7 times 4, which is 28 degrees. This time we have to indicate units, and I should have mentioned this as well for number 11. We do have to indicate units of measure. Angles are measured in degrees. The side lengths we don't have a measurement for. We can say units, but as it's unlabeled here, we can leave it unlabeled there. But we have to mention degrees when it's there. That was the converse of the angle bisector theorem. And that is number 13. Number 14, remember we're going to number 38. Number 14, we need the length of segment FG. We have angle bisector here by the congruent marks. That makes these two parts congruent as G is equidistant to the points F and H, sides of the, points on the sides of the angle. Shows it's on the perpendicular part. That means we know that it's the part that's equidistant. So I can set x plus 11 equal, I'm going to turn off my heater, equal 3x plus 1 and solve for x. I'm going to subtract x from both sides. Subtract 1 from both sides, and divide both sides by 2. We get x equals 5. We have to find the length of FG, segment FG right here. So we're going to substitute 5 in for x. So we get FG equals 5 plus 11, which is 16. Just 16 units, whatever it is. Let me pause this thing. I'm going to turn off my heater. Okay, so I'm not sure what humming my mic ever picks up, what sounds it picks up, but I heard humming before. I don't anymore. Sorry if you heard humming. Glad it's gone. All right, and now I'm not going to be cooked out anymore. All right, in exercises 15 and 16, tell whether the information in the diagram allows you to conclude that ray EH bisects angle FEG. Explain your reasoning. I'm going to assume that one is and one is not. I don't know. That's good textbook writing if they have one that is, one that's not. So, okay. Is EH the bisector of the angle? So we do have the ray that's drawn, and we can see there is this point H, which shows the diagram with equidistance to these two things, and they are on the perpendicular portion. It's showing that the distance is perpendicular. It's good that they do that. Therefore, yeah, this is going to be enough information. This is the converse of that theorem. Totally. Explain your reasoning, and I guess I got to type it out. So, or that's how I'm going to choose to write it. H is on the ray that divides the angle and is equidistant to points on, to the sides of the angle, noted by, this is important, noted by the perpendicular symbols. See, the perpendicular symbols are noting that you found the shortest distance to there, noting that they are both the same distance away. And that's an important aspect that kind of gives away what it is that you're talking about. Therefore, it is on the angle bisector of that angle. All right. Okay, cool. Let's see what the other one is talking about, number 16. So on number 16, you have, looks like, well, oh, okay. So it looks like the same drawing, but what's the exception? What's missing? It doesn't have the right angle symbols. And that's a huge portion of this because, once again, I'm going to do that kind of thing where, like, let's draw something that makes an exception to this, something that would not be indeed an angle bisector. And the only way for me to do that is to make it not an angle bisector. So if I make it not an angle bisector here, well, excuse me, I don't want to do it that way. I'm going to make it look like, listen, it could be the angle bisector, but here's the information that they're giving us suddenly. They're giving you something that says, you know what, hold on, I got to do this the other way. You don't draw the bisector yet, right? What I want to do is give you points that are, I want to give you the counterexample, but I can't do it right. I got to give you two lengths that are the same distance. Let's say this, like this, and this kind of looks same distance-esque. Not really. Let me do that. Let me draw it a little deeper. Okay. Those look same distance-esque, right? Right? So that means this and this are congruent to each other. Okay, fantastic. So here, therefore, here's my point H, right? That's kind of what they're saying, yeah? Now, the question is that point on the angle bisector? Well, let's draw through that and see. Like that. Is that the angle bisector? Does that look like it's going through that middle? And don't say yes, because maybe I didn't draw it extreme enough. But does that look like it's on the angle bisector? No, it looks like that's a more acute angle. Let me erase these now. No, it looks like this is a more acute angle than that other one is, right? This looks smaller than that. Because it is. It's not the angle bisector. So it's that kind of thing that just because those are equal distances, we need to know that those are the same distances away from those points. That those are the shortest distance away from those points, that it's on the perpendicular bits. That's the part that needs to be certain. So no, there's not enough to conclude it here. Although H is shown to be equidistant from points on the sides of the angle, there is no guarantee that each of those are the shortest distances to those sides of the angle, or those same those same reference points, basically. The angle. Perpendicular symbols missing. Therefore, there isn't enough information to conclude. H is on the angle bisector. So we can't take those perpendicular symbols for granted. They're there for a reason. They're there to talk about that shortest distance stuff. I'm sorry, that was number 16. Sorry that I didn't move this over. Okay. Let's move forward. Numbers 17 and 18. Tell whether the information in the diagram allows you to conclude that the length of segment DB equals the length of segment DC. Explain your reasoning. Number 17 looks like it's falling under the same trap that number 16 did. I don't have, in fact, you see number 18? What's the difference between number 17 and 18? The perpendicular symbols. And this is the all-telling thing that D is equidistant to the sides because the perpendicular symbols are showing the shortest distance to the sides. I don't know what things we're talking about here, therefore, I don't know how long these sides are. Right? B, for all I know, see, B isn't in an arbitrary place. B, for all I know, could actually be right here. We don't actually know where B is. We just know that B is a point on the side. So no, those don't look the same anymore, right? That's a much easier counterexample for me to draw. And that's hard for people to get because they're like, well, they drew B right there. That's not the point. It's not about where, it's not assumed to be drawn to scale. We go by what's marked or what's told, not by how they drew it. And there's a big difference. There are only so many things that we can infer from things, like when lines are straight and things like that. But when they mark something to be true, okay. So anyway, I just want to make sure you note that. So number 17 is going to be no, you can't conclude it. No, you cannot conclude it. Because that D is equidistant. Excuse me, that DB equals DC. B equals DC. Because D is not necessarily equidistant. Excuse me. D, the segments, because B and C, shoot, how do I want to say? I just mentioned, because the perpendicular signs aren't there. Because, I don't know if those are called segments. The segments are not perpendicularly intersecting with the sides. Basically noting that those are the shortest distances that we're talking about, right? So it's just not enough information. Whereas number 18 is yes. I mean, for all the reasons here. It totally fulfills the perpendicular bisector theorem. So I'm just going to say yes because of the perpendicular bisector theorem. Bisector theorem. And I'll put in parentheses kind of the whole perpendicular symbols indicate shortest distances for both segments. Okay, so that's an important bit that you have on number 18, which I didn't move it over to there as well. They're really hinting to you at why those perpendicular symbols are so important. I'm very glad that they did that. Okay. Numbers 19 to 22. Write an equation of the perpendicular bisector of the segment with the given endpoints. Interestingly enough, I didn't think we'd have to graph anymore. And I didn't realize going through the example that we would get examples like this. And by the way, you don't have to graph it. Maybe they even expect you to do it without a graph, and I can confirm with a graph that it works. Let's start without a graph. And then let's work with the graph to show that it is indeed exactly everything that we wanted. We can do some with and without. I think that's really nice to be able to do. So on number 19, we have the points M and N. That's my ampersand, by the way. And N. I do want to give you the visual later so you saw exactly what we found here. But what we want to do is find the midpoint. I am not happy that they gave M as one of the letters here because I like my midpoint being M. Gosh darn it. So I'm just going to say midpoint. The midpoint is averaging your X values of 1 and 7. We add 1 and 7 divided by 2. And averaging your Y values of 5 and -1. We add 5 with -1 divided by 2. And we find the middle value of your X's and your Y's. What's the middle of 1 and 7? You average them. What's the middle of all that. So 1 plus 7 is 8. 8 divided by 2 is 4. 5 minus 1 is 4. 4 divided by 2 is 2. So the midpoint is at 4, 2. Now this is a reference point. This is an XY value that this line goes through, and we're going to use that. Now I'll do it the same way that the examples did. We're going to use that in the equation that we make to find out what the y-intercept of this equation is. Now the other part that we need of this, to write the equation of the line, is we need the slope. We need the slope of this line. So we need to find the slope of segment MN, and then we're going to take the opposite reciprocal of that slope. And here's the tricky part about this. You know our equation is y equals mx plus b? M is slope as well. Thankfully, it's a lowercase m, but the slope, this is a good thing I didn't use lowercase m for this, the slope of segment MN is going to be, you might know this formula, y2 minus y1 over x2 minus x1. You got to find the distance, the change in y, and the change in x. And I promise you I'll do graph ones later, but I can't guarantee you have graph paper. I'll attach it down below. But I can't guarantee you have graph paper for this either, right? So this is just all that, like, can you understand the physical concept of what's happening here? So this is -1, also known as -1 over 1. That's the slope of this segment. Now the line that's perpendicular to it will have an opposite reciprocal slope. So I'm going to say the slope of the perpendicular, that's kind of the upside down, that's the symbol. Slope of the perpendicular one, positive 1 over 1, flip the 1 and 1, you still get 1. So the slope of the opposite reciprocal is 1. So as far as y equals mx plus b goes, right now our equation looks like y equals 1x plus b. Or y equals x plus b, right? I don't even need the 1. And forget the 1. I need the b. X and y, we're going to temporarily substitute 4 for x and 2 for y into these equations here to solve for b. So we're going to get 2 equals 4 plus b. And subtract 4 from both sides, you get b equals -2. So your final equation here is y equals x minus 2. Y equals x minus 2, like that. Okay. Did we find everything appropriately? Let's draw these and draw that line and see if it worked. In other problems, I don't know. I'm going to use the graph sometimes, and I won't use it sometimes. Maybe for the odds I won't. For the evens I will. Something like that. How does that sound? Sound pretty good? I'll give that a shot. Maybe I should have started with the graph so you didn't get too confused. The point M is on 1, 5. Here's M. N is at 7, -1. N is at 7, -1. Here's the original segment that they are talking about. Now, we just made a line y equals x minus 2. Excuse me, we came up with that equation. Y equals x minus 2. Y-intercept of -2. Rise, run 1 over 1, like this. Now, they're asking, is this the perpendicular bisector? Did this divide this? Did it intersect at its midpoint? And is it intersecting with it perpendicularly? Those are kinds of the two questions that are being asked. And this is a line, so I'm going to draw this thing forever through. Y equals that. I mean, to me, I'm asking you, does it look like it is? Because I think it does look like it. So it looks like this thing intersects at a right angle. And it looks like that this part is congruent to this part. Just by appearance, we can probably say yes. Now, in a visual sense, now we can say what we actually did. We found the midpoint here at 4, 2. 4, 2 is halfway between 1 for m and 7 for n for x, and the 2, the y value, is halfway between 5 for m and -1 for n for the y's. And then we also calculated the slope of down 6 over 6, which is also down 1 over 1, -1. The opposite reciprocal is up 1 over 1, and that's the way that it intersects with it perpendicularly. And how did we get the y-intercept of -2? We plugged in the x, y, 4, 2 as a reference point for this equation, solutions to it, and found the b that associates with it. There are other couple ways we can do it, but that's the way that we went about, which it totally works. Okay, that is number 19. Let's move on to number 20. This time, let's do it on a graphing basis. I'll give you both versions of it, and hopefully you can follow along in a way that, like, my teacher wants me to do this. My teacher makes me do that. Well, hopefully you can look at both now and say, which way do I prefer? Not which way do I prefer? Can I use the method that you just did on one and apply it to the other one, even if you didn't teach it that way? I think that'll be nice to see. All right, Q is at -2, 0. Oh, you know what the problem with this one is? Hold on. Okay, this isn't going to be a perfect thing. But Q is at -2, 0. R is at 6, 12. Here's the problem. 11, 12. Okay, R is at 6, 12. It's all the way up there. Hopefully that's all right. I don't want to get the taller graph because it doesn't have numbers on it and because I already got this one up. Okay, there's segment QR. Let's come up with the line perpendicular to it. Let's start with the midpoint. And what's nice with my graphing tool is it looks like the midpoint's probably going to be wherever that line thing is right there. Now, a way you can find the midpoint without calculations is by doing, and this is actually helpful in two ways. You know that slope stuff we're talking about, like rise over run? How much do we rise for Q if you counted this? How much do we go up and how much do we go over? Well, how much do you go, and I promise I'm talking about midpoint. We're going up from 0 to 12. We're going up 12. And from negative 2 to 6, we're going over 8. That's a rise of 12 and a run of 8. The midpoint, you should be going up half those amounts. Half of 12 is 6. 1, 2, 3, 4, 5, 6. 6. And over half of 8, which is 4. 1, 2, 3, 4. And you should be landing on a point, right? And this time I'm going to use M. That midpoint. The midpoint is at 6,2 or 2,6. 2,6. Now, do I actually need that midpoint this time? Not necessarily. It depends on how we're going to work out the slope aspects of this, and it depends on whether the y-intercept's an integer or not. I sure hope it's an integer, but it depends on whether it actually is. So that midpoint is at 2,6 right there. Now, the next part, let me write M in a different spot because my line's going to go through there. The next part is talking about the opposite reciprocal slope. We can see that the slope of line QR is 12 over 8, but that can reduce. That can reduce to 3 over 2. Okay, up 3 over 2. That means the opposite reciprocal slope, you have to switch the sign to negative and flip this fraction to 2/3. The slope is negative 2/3. So if I want to write the equation of the line, they want it in slope-intercept form, not point-slope form. I'm not saying whether they want one the way or the other or not. I actually don't know. You know what? We might need this. This y-intercept's a fraction. Okay, so I will have to do some calculations here because the opposite reciprocal is negative 2/3. Here's the problem. I can go down 2, right 3, things like that, and make the drawing, and then therefore up 2, left 3. But notice it's not going through an integer y-intercept. I didn't actually anticipate that. So I'm drawing this for you, but this didn't get our y-intercept answer perfectly. I could tell you what it is, but I want you to say you be asking how I got it. So we got to calculate it. Now, here's the thing, guys. They said write an equation. They did not specify form. If you used point slope form, which is y minus y1 equals m times x minus x1, where m is the slope, and x1, y1 is a point that you know, for example, 2 and 6, then you can substitute those straight in, and you'd get y minus 6, that's your y1, equals m, negative 2/3, times x minus 2. This is a valid answer to that problem. I have to do no more work. I didn't have to find the y-intercept. I used the point that I had that wasn't necessarily the y-intercept and plugged it in there. If you need slope-intercept form, you could also take this equation, distribute the negative 2/3 into both of these, and add 6 over. Very valid way to do it. We can also use the way that the textbook just did previously, but guys, the y-intercept is going to be a fraction. There's no way that you can't, I'm showing you right here, it's going to be a fraction. So what else could you do? We can do the way that they were doing it before. Y equals mx plus b, negative 2/3 x plus b. We'll substitute 2 for x and 6 for y into this equation. 6 equals negative 2/3 times 2 plus b. Negative 2/3 times 2 is negative 4/3. And this is nobody's favorite thing. I'm going to add 4/3 to both sides. 6 plus 4/3, but here's the thing. I'm going to make 6 a common denominator by multiplying top and bottom by 3. So I'll make it 18/3. We're going to add 4/3 to it. That'll equal our b value. B is going to be 22/3. That's also 7 and 1/3. That's where this thing's crossing at. It's crossing at 7 and 1/3. 22/3. And if I distributed the negative 2/3 over here and added 6 over it, you'd be getting the exact same answer. So this equation also can be written as y equals negative 2/3 x plus 22/3. Not the best time on number 20 to have a fraction y-intercept when I was trying to draw it by graph. I'm hoping that number 22 would give me a different setup. We'll see. Either of those two answers are acceptable. And other, I'm only going to use point slope form on ones that it kind of forces me to do it, such as that one. So we'll see if another one does. I won't know off the bat on number 21 because I'm going to do this without the graph completely this time. Number 21 will have points U and V. Okay. We need to find the midpoint of these two guys, which we're going to average our x's, average our y's, like so. That'll get you 6 over 2, which is 3, and 12 over 2, which is 6. So your midpoint is at 3, 6. That's our xy. We can use to plug in to an equation to find the y-intercept, or use for point slope form, which we might have to do. The slope of segment UV is our y2 minus y1, 8 minus 4, over x2 minus x1, 9 minus negative 3, which is 9 plus 3. 9 plus 3 is 12, and 4 over 12 is 1/3. Okay, there won't be a y-intercept issue here. So 1/3 is the slope of segment UV. Well, the opposite reciprocal slope, we got to flip the fraction and change the sign. It'll become negative 3. We're going to use this. So as far as the equation goes, we are going to use in y equals mx plus b form. This is y equals negative 3x plus b. We will substitute 3 for x and 6 for y. So 6 equals negative 3 times 3 plus b, or 6 equals negative 9 plus b. If I add 9 to both sides, I am going to get b equals 15. So your full equation now with your slope of negative 3, the perpendicular opposite reciprocal slope, and b of 15 is y equals negative 3x plus 15. Let's trust the process on this one. I won't draw the graph to confirm it. Let's just state that it was as intended. I'm going to trust it. I hope I was correct. But that's the equation of the line that's perpendicular. Excuse me, it's not just perpendicular. It's the perpendicular bisector. It is intersecting through the midpoint, and it is perpendicular to it. Both those parts are obviously very crucial. That's why we did the midpoint. Number 22. This time let's do it with the graph, and let's just hope and pray that it is that you can just draw it out and make it work. Let's check it out. At least these will fit on the graph this time. Y is at 10, negative 7, just barely, but it fits. But here's Y. And Z is at negative 4, 1, like that. Here's Z. So here's the segment that will be perpendicularly bisected, excuse me. The midpoint should be the halfway mark of what's being counted. So what's great about this, once again, that I stated is we are killing 2 birds with 1 stone. See, this is what the formulas don't do. We are going to be killing 2 birds with 1 stone by doing this rise-run concept right here. However much this is, not only represents the slope, but also half of this represents how much we can traverse to find the midpoint. So we go down from 1 to negative 7. We're going down 8. We're going over from negative 4 to 10. We're going over 14. That represents our slope. Obviously, we're going to reduce the fraction, but the midpoint will be half that distance. Sorry, I just messed something up. Will be half that distance. So instead of down 8, let's go down 4. Instead of over 14, let's go over 7. And boom, you land on this midpoint right here. This M. Boom. Right there. The M, the only problem is I think this is going to be a fraction y-intercept again. But the M is at 3, negative 3. That's our midpoint. I'm going to kind of erase all that other stuff there, at least the green that's right there. Now your slope is that next bit, right? The slope is negative of segment ZY is negative 8 over 14, which is negative 4 over 7 when reduced. So the opposite reciprocal slope, the perpendicular one, is positive 7 over 4. We're going to be having another fraction y-intercept thing here. I really wish I flipped these problems. I wish I looked at this. See, I don't look at them beforehand. Up 1, 2, 3, 4, 5, 6, 7, and over 1, 2, 3, 4. I didn't look at an answer key if there is one somewhere. And go down 1, 2, 3, 4, 5, 6, 7, and over 1, 2, 3, 4, like that. So this is going to be another kind of, I'm going to have to calculate some stuff with you, but at least we get a graph that kind of shows what it is that we have. I'm not apologizing for this work. It's still proper work. You just got to calculate more. You can't let the graph do it all for you. I sort of can. I can do enough to conclude that I believe it's going to be at this, this, and that, but I don't know as a for sure. So let's go ahead and see what we got this time, right? So in a y equals, now first of all, you can use point slope form. We have all the information. We have this, and we have our x1, y1. So I'm going to write that just like I did last time. So y minus y1, subtracting negative 3 is plus 3, equals m times x minus x1, x minus that 3, is a very valid answer, and one that I would likely be using because I'm done. But in slope-intercept form, and as far as slope-intercept form goes, you could either, like I said, distribute 7/4 now and subtract 3 after, or write it in that other form where we have y equals 7/4 x plus b. Substitute 3 for x, negative 3 for y. Oh, I don't want that y right there to confuse you. Let's just move these over. Substitute 3 for x and negative 3 for y. And we get 21/4 plus b over there. I just subtract 21/4 over with negative 3. Negative 3 is also negative 12/4. So negative 12/4 minus 21/4 is going to give you negative 33/4. And that's the b value. So your equation here could be y equals 7/4 x minus 33/4. 33/4 is negative 8 1/4. Does it look like our graph crossed negative 8 1/4? Pretty much. I mean, pretty much. Don't say it crosses negative 8 because it just doesn't. If it did cross negative 8, we would have hit that integer value. This is a reduced fraction and it didn't hit it. So we would have had a point there and it's not. So negative 8 1/4 seems to make a lot of sense, and that seems to be a good answer. And that is your numbers 19 through 22. Again, I just wish I reversed these and did the graphs on these because we would have landed on integer y-intercepts. Would have been perfect. These would have been perfect to straight up calculate to begin with. I should have assumed that was going to happen, but I don't know how. All right, error analysis. Exercises 23 and 24. Describe and correct the error in the student's reasoning. Story of my life, right? Students always been making errors, and I say, no. All right, because the length of segment AD equals the length of segment AE, I agree. Ray AB will pass through point C. I don't know anything about that point C. Now, I don't think an inherent error is in their typing that they didn't mention that this is, that they neglected to mention it's perpendicular. Let's assume that we can see it through the drawing. We understand that. I don't know where point C actually sits. We don't know any information about point C. I know that point B is, equidistant to these two things, perpendicular bisector, blah, blah, blah. I know all that. I don't know that C is on the perpendicular bisector because we don't know that these two things are equidistant. So when it says correct the error, I don't know what to correct because there's just not enough information in the problem to make that conclusion. I don't know. C, the student is leading the false assumption that C is on the perpendicular bisector of the segment in question. It's not in question. Of the segment being perpendicularly bisected. Yeah, they're leading the false assumption. C, there is no information that shows C is equidistant to points D and E, to the endpoints of the segment. I don't know how to correct it. If we had this information, then you'd be good. If you had information that points A, B, and C are collinear, then you'd be good. I guess the thing we have to say is this is inconclusive. This is correction. This is inconclusive. It's not enough information. I'm not going to add more information to the problem. I don't know what kind of information they wanted, or they should have given you, but that's the correction to it. There's not enough information to conclude that C is on the perpendicular bisector. Come on, student. Number 24. Why? How come? By the angle bisector theorem, x equals 5. We do have an angle bisector here, and, well, this shows the perpendicular portion here, but this does not, right? So this is one of those, this is inconclusive things as well. They're saying correct the error. If they're saying correct the error, or excuse me, if by correct the error they mean tell them what the correct answer is, there isn't one in the sense that it's inconclusive. So I don't know what to say with that either. But it's the same kind of thing. Segment PB, and pretend like there's a segment bar above for a moment, but segment PB does not show perpendicularity with the side of the angle to indicate the shortest distance as PA does to the other side of the angle. Therefore, even though ray CP, and I'm going to draw all the symbols after, is an angle bisector, P is not necessarily... P is absolutely equidistant to the sides, but PA is not necessarily the same length as PB. I don't know where B actually is as a point. I don't know what's on the perpendicular shortest distance point location. So let's see. How do I want to say that? Therefore, even though CP is an angle bisector, PB doesn't necessarily, and I have a symbol for this, does not necessarily equal, or is it this one? Not necessarily equal PA. I'm just gonna say that. And in correction, this is inconclusive. There's not enough information there. You would need the other perpendicular symbol. And indeed, you would need the perpendicular symbol for both. I think we brought that up before. So I'm going to put a thing there, and a thing there, and a thing there. These are about length, so I don't need them there. All right, that's number 24. Let's keep moving forward. How are we doing on time? Over an hour. Okay, number 25. Modeling mathematics. In the photo, the road is perpendicular to the support beam. Okay, so they don't indicate perpendicularity, so let's do that. The road is perpendicular to the support beam. And segment AB is congruent to segment CB. Once again, they don't mark that. I guess it's up to us to mark. I don't know why I'm doing 2 marks, but that's okay. Which theorem allows you to conclude that segment AD is congruent to segment CD? Well, and they don't ask us to explain why, so I'll just do it verbally. This means that segment DB is a perpendicular bisector of segment AC. Therefore, D is equidistant to the lengths, or to the points A and C by the perpendicular bisector theorem. And I will happily write it out. Perpendicular bisector theorem. Ha 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 ha. And I believe we proved that one. We didn't prove the other ones, did we? Which must mean we got to prove them later, or they are on another page of notes. I don't know where these pages end. So, yeah, we will find out if we are the ones who have to prove that in a bit. All right, number 26. And that's fine if we have to. It's just their triangle congruence proofs with CP/CTC. That's what a lot of proofs are. Modeling with mathematics. The diagram shows the position of the goalie and the puck during a hockey game. So here's puck, here's goalie. The goalie is at point G and the puck's at point P. A, what should be the relationship between ray PG and angle, so let's draw a ray, and angle APB to give the goalie equal distances to travel on each side of ray PG? If there was a ray drawn here, in order for it to travel equal distances, meaning those shortest distance kind of thing, like boom right there, equal distance here, and boom right there, equal distance, what would have to be true about ray PG, excuse me, is it would have to be the angle bisector of angle APB. So that's the end crux right there. That's what we need for that. So for number 26, part A, PG, ray PG, would have to be the angle bisector. I think I need a thing here, otherwise it's a vector. The angle bisector of angle APB. You probably wish I typed that, but too many symbols. Part B, how does the measure of angle APB change as the puck gets closer to the goal? Does this change make it easier or more difficult for the goalie to defend the goal? Explain your reasoning. Okay, well, think about it this way. Pretend like point P was where point G is. And keep in mind, it's on the angle bisector, so that's a valid place for it to be. Pretend like this is point P now. Look at this angle now. Is that angle, not the lengths, is the angle a bigger angle or smaller angle? Or better yet, let's go farther out. Let's say that the puck was way back here. Is this angle out here bigger or smaller? The farther away you get, the smaller the angle is. The more error the less room for error that you have to make a wide shot and not make your goal. The closer you get, the greater the angle will be, the more room for error that you actually have. So the closer you get, the wider the angle. So how does measure of angle APB change the puck gets closer to the goal? It gets bigger. We're going to say that. Does this change make it easier or more difficult for the goalie to defend the goal? Oh. We didn't get to that part. Depends on how the goalie's working with this, because that's a tough question to answer, because you get closer to the goalie like this. If the goalie doesn't change, I mean, you ask me. The goalie has little, you have little room to shoot. I understand if you're, that's a tough answer to question in context, because we're not sure if the goalie moves. Now we're talking about reaction time. We're talking about you close the gap from the goalie, so the goalie's amount of distance it has to travel has lessened, even though the angle got bigger. So when they're saying, does the change make it easier or harder, are they asking, does the change of the angle, because here's the word change, how does the measure change, does this change? Are they talking about that, or are they talking about just making the puck closer change? It's not, this is not an easy answer. Is the goalie moving with the puck? Is it moving in that distance there? 'Cause I don't know if I can answer that second question properly and logically. This is the same thing that you would ask, because I coach softball. This would be the same thing for asking, if you move the infielders in closer to home plate, why don't infielders stand, like right next to the batter and just field there? Because there's a lot less room that the batter can hit it past you there. Well, now a batter can hit a bigger fly ball and it can go past them. If they hit it so hard, it can not only hurt your defender, but defender has less reaction time. I'm sorry that I'm talking about semantics of a problem more than just the math itself. I don't know how to answer the second part of this question, and I apologize to you guys for that. So it's all contextual, and this is something I can type out. So let's start with this. As the puck gets closer to the goal, as the puck gets closer to the goal, the measure of angle APB gets bigger. Does this change make it easier or more difficult for the goalie to defend the goal? Not an easy question to answer. I'm gonna say, although the angle gets bigger, the puck is closer to the goalie. Therefore, the goalie has less distance to travel to need to defend the goal. Therefore, it could be easier. However, because the reaction time lessens and the angle of the shot can widen, it also may prove to be more difficult. I'm just going to go all directions with this. The question was fine to begin with. They should have asked about room for error for the shooter. They should have not asked about the goalie. Tough question to answer. Number 27. Use a compass. Oh, I don't know if you guys can do this one. I don't know if I remember how to use the tools on my thing with this. Use a compass and straight edge to construct a copy of segment XY. Did they teach you compass construction? Construct a perpendicular bisector and plot a point Z on the bisector so that the distance between point Z and XY is 3 centimeters. Measure, oh my goodness. Okay. This is not, okay, I'm just going to copy the segment. There's nothing about this that is going to be perfect with what you guys do, even if you have a compass and straight edge, because number one, I can't measure 3 centimeters on this thing. I can makeshift a ruler thing that I have, but you're looking at a phone screen. I'm looking at a computer screen that's inches wide. Nothing here is going to be of any sort of perfection. You have to keep that in mind. Number two, I don't know if you have a compass and straight edge. You should have a straight edge. A straight edge is like your ID card or your phone. You don't need a ruler. But I don't know if you have a compass. Number three, I don't know when it was taught. Okay, I'm gonna do this one. I swore, an oath that I'm gonna do every problem. Here's my tool. I'll talk about it very briefly, as if maybe you've learned it before, and we'll do the best we can. Okay, to construct a perpendicular bisector, you'd like to place your pivot on both endpoints and widen this. The farther you widen it, the better. But widen this past the halfway point of the midpoint of your segment. And then draw yourself arcs on both sides of this. I got to keep this width the same. So this 211, I got to keep the same. So I'm going to take this width over here, go on the other side. Let's flip this guy. Give me 1 second. Oh, I can't flip it. So I'm just going to rotate it. Rotate this guy. Whee! And I'm going to draw another one here. Where these things intersect, up and down right there, where those intersect, you want to take your straight edge and draw a line through that. I'm going to draw it in blue. This line that this goes through represents the perpendicular bisector of this thing. You can tell something's not to scale perfectly. It's probably because the way that these are placed on the pivots isn't perfect. So let me place this a little farther over, like that. Maybe still not perfect, but maybe a little bit better. So let's try that this time. If drawn properly, it's not perfect. Let me try that one more time. Where's my error here? Let's rotate this back to start. Okay, let's make it look more like that. Let's see how this does. Okay, last time. The reason I say the wider the better is because there's less room. See, this is the puck goalie thing. There we go. There's less room for error in precision if you're farther out when you end up drawing your line. It's closer to the actual possible thing than not. There'd be a lot more error if I made them a lot closer. So there's the line that goes through those two things right there. This line should be going through the bisector of the segment, and it should be perpendicular, which is pretty boss in both fronts. Now, I made a perpendicular bisector using compass constructions. That means boom and boom. Okay, now they say plot a point Z on the bisector so the distance between point Z and segment XY is 3 centimeters. Remember, the distance is the perpendicular distance. So now I'm going to go to my ruler tool. I forget where it is. Go to my ruler tool. It popped up right here. I'm going to find the 3 centimeter mark. I'm not going to change the scale. I don't know how to rotate this though. Here, make it go vertical. 3 centimeter mark is there, so let's go. Oh, cool! It's like right on this line, like right there. Okay, so here's the 3 centimeter mark. Boom. Am I drawing on the ruler? Okay, there it is. And I'm going to call that point Z. Sorry about that. Okay. Okay, let's get rid of the ruler. Let's get rid of the compass. Let's get rid of these arc marks even, or let's make them very transparent. Okay. Measure. Oh, I should have gotten rid of the ruler. Let's go back. Measure XZ and YZ. Which theorem does this construction demonstrate? Well, it's going to demonstrate the perpendicular bisector theorem. But what we should be getting here are equal distances. Now, everyone's x, z, and y, z will be different because I copied and pasted it from the book and I resized it. So who knows what my x, z, and y, z is. Yours isn't going to be the same as mine. But the point is, these distances should be the same. These should be the same. So I need my ruler for this. I didn't actually need the segments to be drawn, but I wanted to show you where I'm going to do my measurements because this rotation is not going to be pretty with this tool here. And I cannot resize, I should not resize my ruler when I'm doing this, otherwise it doesn't work the way you want it to. So my distance from x to z is about 5.3 centimeters. 5.3 centimeters. And if this is all done correctly, then this other one should also be about 5.3 centimeters for z to y. So let's rotate this downward. Let's line it up, up, up. Let's stick it there. Let's do a little bit more upward like that. And from here, z to y, it's about, that looks like 5.2, 5.3. I'm just going to call it 5.25 on both of them, whatever. 5.3. 5.3 centimeters. Okay. Here's a way, and I like that one. It's a physical version. The construction is there so that you guaranteed that you made a perpendicular bisector. There's no wiggle room for error, specifically with the perpendicular part. It's easy to find a midpoint. It's hard to draw something that's perpendicular, perfectly perpendicular, even if you have, you know, a straight right angle thing to do it. So we're just getting everything in there through compass construction and showing that the theorem demonstrates that the perpendicular bisector, point on the perpendicular bisector is equidistant to that point. This demonstrates the perpendicular bisector theorem. Probably don't have enough room to write it. Okay, there's number 27. Nice and fun. Okay, number 28. Writing. Explain how the converse of the perpendicular bisector theorem is related to the construction of a perpendicular bisector. Well, we kind of just talked about it. But the converse... Oh, to the construction. I see. Oh, they don't actually mean compass construction. I see. So let's see. Explain how it's related. Okay. If you have a point that is equidistant to both your endpoints, then drawing, then either, well, let's see. Oh, timeout. Hold on. I do think they do mean construction. I think it does have to do with this problem. So let me go back. So remember when I drew these arcs, these arcs in black. The importance of the arcs was to highlight the fact that where they intersect, first of all, they had to be the same size. The important part was to highlight the fact that both the top and bottom are points that are equidistant. See, it's not just z that's on the perpendicular bisector. These points are also on the perpendicular bisector too. That's how I drew it, right? I drew it from these. These are also equidistant to there. So the perpendicular bisector, the compass construction created equidistant points. And because it created two of them on top and bottom, drawing them guaranteed the whole thing, right? That makes the converse thing happen. So it guaranteed that this line would have been the perpendicular bisector. So yes, this construction is what they're talking about. So let me go back, so let me backtrack this. When in compass construction, the arcs, the drawn arcs, the points of intersection of the drawn arcs represent points that are equidistant from the segments. Now listen, how could they not be equidistant from the endpoints of the segment? Endpoints of the segment. How could they not be equidistant from the endpoints of the segment? I used a compass that would make a radius, a circle radius, on an endpoint. Any part of the arc is equidistant from there. The point is where they intersect are both two sets of equidistant points. So how could they not be equidistant, right? Therefore, the converse of the perpendicular bisector theorem also indicates that those points should be on the perpendicular bisector of that segment, which is why we drew that line. Which is why we drew that line that went through the blue one, right? Okay. Number 29. What is the value of x in the diagram? Okay. In this diagram, we have several right angles. Okay. Now, the only right angle, actually, all of them matter. These right angles only matter to indicate that whole converse of the angle bisector theorem, that these equidistant, this point is equidistant properly to those things of the bisector, so we can ignore the right angles here on out, that everything's going to apply the converse thing, which just means this is congruent to this. Now, those are congruent, but it's not so much that they're congruent that matters. Well, it is. But that this is a right angle here as well. Because this bisected it, it doesn't just make these congruent, it divides the angle into two. So 3x minus 9 is 45 degrees. How do I know? Because 45 is half of 90. This is a right angle. These angles are complementary to each other, but they're also the same. So two 45s make 90, so half of 90 is 45. So we can add 9 to both sides, and we can divide both sides by 3, and we get x equals 18. Now, what do they want? The value of x? It's 18. So it's going to be b. It's going to be b. It's b. Okay. Number 30. Which point lies on the perpendicular bisector of the segment with endpoints m of 7,5 and n of negative 1,5? All right, it's kind of a tricky question because it's not asking what's the midpoint, but we might have to do a lot of stuff to figure out which one this is for sure. We could, now listen, if they had us draw it, we could probably look at that answer and say, yeah, it's that one. Let's draw it after the fact and guarantee that it worked out the way it did. But let's do more of a calculation version of this. I can get this in full. Let's even see if one of these is the midpoint. I don't know. The problem is, of course, they use m as one of the letters. M is 7,5. And n is negative 1,5. So, excuse me. So, oh, this is an easy thing. The 5s, they're both 5. So, the midpoint, halfway between 7 and negative 1 is 3. That's the x, halfway between. The y value is still 5. That doesn't change. Okay, this answer might be a little easier than I thought. Because this is a horizontal straight line. I don't need the visual to know that for sure. But this is a horizontal line because the y's are the same, right? That means the perpendicular line, the perpendicular bisector, going through 3,5 will be vertical. But what is a guarantee? The guarantee is that, well, first of all, the equation of the line is, it's not y equals mx plus b. The equation is x equals 3. I will show you this visual after. It's a vertical line. Which means the only answer, and I haven't looked at them yet, the only answer that's possible on here is the one with an x value of 3. No other one's possible. So which one is it? B. So B is the answer. Now, the work is a little iffy. So let's actually go to a drawing. Let's take a graph and talk about what I was talking about. I thought it was going to be slanted lines. So M is at 7,5. N is at negative 1,5. So here's M, here's N, here's that segment. Okay, the midpoint, that's a thick segment. The midpoint is at 3,5. This guy right here, 3,5, boom. The perpendicular line is vertical because this line's horizontal. So if this line's vertical, which of these points is going to be on that perpendicular bisector? It's one where x is 3. 3 comma something. Right? So 3,9 is on there. Here's 3,9. That is on the perpendicular bisector of those two guys. Obviously not 2,041 or 1,3. So it's gonna be bay. One more time there. Number 31, making an argument. Your friend likes to argue math. Your friend says it is impossible, impossible for an angle bisector of a triangle to be the same line as the perpendicular bisector of the opposite side. Is your friend correct? Explain your reasoning. I don't know where your friend got that idea. Let's go ahead and take a look at this. Let's look at it, what he's talking about. Let's say that I have, some angle bisector, like this guy. This angle bisector right here. You see how it bisects the angle? See how it nicely divides this into two, that's better, two congruent parts right here and right here? They're saying, you know what? It can't go in between these guys right there to make these congruent. No way can it. To that I say, huh? Huh? No, your friend's not correct. Explain your reasoning. There's a triangle proof concept that I'll explain. This is a right angle. In the case, to be a perpendicular bisector, we have to start with the concept of perpendicularity, right? So let's not assume the bisector part yet. Let's assume the perpendicular part. Why not? We can do one or the other, because you can always draw an altitude in a triangle, or you can always draw a segment bisector, a median in a triangle. So one or the other is going to kind of work out. So let's assume the bisector part for now. The perpendicular part. Okay. Well, we know these two parts are congruent by definition of angle bisector, and these two sets of angles here are congruent because all right angles are congruent, and that's how perpendicularity works, that they'll both be 90. This segment is congruent to itself by the reflexive property. Therefore, this triangle here is congruent to this triangle here using angle-side-angle theorem. Angle, side, angle, and angle, side, angle. By the corresponding parts of congruent triangles are congruent concept. This segment, therefore, must be congruent to that segment. Therefore, this will be a perpendicular bisector. And that's it. That's all I have to say. By angle, side, angle, and CPCTC, I can disprove my friend. Now, what kind of triangle, my friend. Now, I don't know if that's what they wanted me to say, so let me go a different route on this. Let's talk about, because this is the kind of triangle it would be, let's talk about the isosceles triangle. In the isosceles triangle, this point is equidistant to these two endpoints like that. So here's the isosceles triangle. That would make that so. If this is an isosceles triangle with that way, then the converse of the perpendicular bisector theorem that states the point that is equidistant to the two endpoints of this segment is also on the perpendicular bisector of that segment. So you can also do this by the converse of angle bisector theorem, perpendicular bisector theorem. Your friend, my friend, is incorrect. So this is true in the case of isosceles triangles, basically. It's only true in the case of isosceles triangles. And equilateral. Of isosceles and equilateral triangles. Okay. Hopefully we're making some sense of that. All right, number 32. Prove the converse. Oh, here they are. Prove the converse of the perpendicular bisector theorem. Hint, construct a line through through point C, perpendicular to segment AB at point B. Okay, I'm likely to use a 2-column proof for this one, so bear with me on that. I'm going to go ahead and make that happen. So on number 32, the diagram's drawn there, and I'll be using that diagram alongside what I'm going to do here. Maybe I can type this out. No, there's a lot of symbols. I will, however, type out statements and reasons. Statements, reasons. All right. Good enough. Okay. Whoops. All right, here we go. Let's kind of put it in the middle. All right, number 1. We have a given that CA is equal to CB. That is given. Now it's also drawn, so that's good. 2, and I forget how they state these reasons, and I apologize if this isn't going to be perfect at all. 2, we're going to construct a line through point C perpendicular to segment AB at point P. Oh, perfect. Draw C perpendicular to segment AB at P. The reason will be construction. By construction. This is telling you to do something. I'm not telling you what's true or not. I mean, I'm making a truth. That's okay. Like, I'm not saying he's the murderer. I'm saying, hey guys, let's look at this camera shot. Like, you know what I mean? Like by turning on the video feed. So we're doing something with the diagram. I should probably use a different color. Let's use, you can't probably see that as blue. Let's use green. Okay. So here's this green guy right here. Let's do that. Let's call this guy Le P. Okay. Now this one will be kind of a lot like the last one I was talking about when I said angle, side angle. This will not be an angle, side angle case, but there's going to be that. So if we draw that perpendicularity there, then we do know that is, I don't know if I have to now say CP is perpendicular to AB because that's what the drawing is. So I don't think I have to make that statement, but I do now have to state that angle CPB and angle CPA are right angles. Okay, they are right angles. That is the definition of perpendicular lines. Now here's the thing. I don't have to say they're congruent per se. Maybe you do. Maybe you do, maybe you don't. I'm going to be using HL, hypotenuse leg, to prove these things congruent. Hypotenuse leg. All you need to say is that the legs and hypotenuse, one set of legs and the hypotenuses in right triangles are congruent. So instead of calling these things congruent, I'm going to talk more about the fact that these are right triangles. So for triangle CPB and triangle CPA are right triangles, this is definition of right triangles. That they have right angles. Stating they have right angles leads to this statement. Now that I have right triangles, I can use an HL proof as long as I can get hypotenuses congruent and legs congruent. Now, statement 1, CA is equal to CB, is not a congruent statement, but statement 5 will be. I probably should have done this as statement 2. But segment CA is congruent to segment CB. This is the definition of congruent segments. Congruent segments have equal measures and vice versa. There's one congruent statement for the hypotenuses. That is my H in HL. That is my H. 6, my statement 6 will be my HL statement. This is going to be an 8 statement long proof. Segment CP is congruent to itself. Segment CP is congruent to itself. That is by the reflexive property. It's a shared side in both triangles. Reflexive property of congruence. That is the L. That is one of the legs that are congruent. Statement 7. I'm sorry. This will be a 9-step proof. There's probably a shorter version of this if I didn't have to do the drawing part. But, or if and I think you got to use HL. I can't see a way that you're not going to. Statement 7, unless I say base angles congruent, isosceles triangle, that kind of thing. I'm not going that route. Statement 7 is triangle. I got it. CPB is congruent to triangle CPA. Let's see. Let's put A first. Triangle CPA is congruent to triangle CPB by the hypotenuse leg HL congruence theorem. Statement 8 now allows corresponding parts of congruent triangles to be congruent, such as these parts right here. Segment AP is congruent to segment BP. This might be a 10-step one. By CPCTC, corresponding parts of congruent triangles are congruent. Let's see. Perpendicular bisector theorem. If it's congruent, now I have to state it's a bisector. So therefore, segment CP is a bisector. Of segment AB by definition of segment bisector. And finally, statement 10, the proving statement. I've proven it. Statement 10, point C lies on, lies on the perpendicular bisector of a segment AB. This is definition of perpendicular bisector. Okay, I'm not going to walk through the whole proof, but let's go through how one statement led to another. The first statement led to my fifth statement. The equal sides means the congruent segments, okay? This drawing, statement 2, is a part of my final statement. Perpendicular bisector, the perpendicular part was part of statement 2. The bisector, statement 9, was the other part of statement 10 right there. But 9 came from 8, 8 came from 7, 7 came from 5 and 6. Okay? And then the perpendicular part led to the right angles, which meant right triangles, which meant I could use HL. So there were all the concepts. So no statement was wasted. Every statement was used there. All right, number 33. We got to prove another theorem. Use a congruence theorem to prove each theorem. Angle bisector theorem and converse of the angle bisector theorem. If they mean, they might mean triangle. They might just mean what we were just doing. Just do another proof. Use a congruence theorem to prove the angle bisector theorem and the converse of it. Okay, let me draw. I'm gonna go back. Give me a second. I'm gonna go back to the notes and copy and paste the diagram because I want the right angles and all that stuff too. So it's gonna kind of be a moment here. Sorry about this, Mike. Copy and paste both of these actually. So one. This might take a moment. Not this, but doing the proofs and stuff. These are pretty long problems. And 2. Okay. Okay, y'all. Sorry. I don't know why you're showing my face. It's not like wasn't doing anything too controversial there. All right. Use a congruence theorem to prove each theorem. So I just put these guys in here. So this is for number 33. So we'll do one at a time. So let me get this one out of the way and start with this one. So part A. Angle bisector theorem. Whoa, okay, wow. No, terrible. All right, so we have some givens. Okay. Gotta figure out where I want to put this. Can I put this? Oh, let me put this over here. Is that okay? Let's just put this here. Right? All right. Statements and reasons. Here we go. Statements, reasons. Okay. Couple givens. Given AD is a bisector of angle BAC there are a couple other givens. segment DB is perpendicular to ray AB. I'll just say segment AB. I'm going to look at them as triangles. And then segment DC is perpendicular to segment AC. Also given. Okay. So we have those, and they're already marked. Now, I'm going to also refer to this will be shorter. Right here, boom, segment congruent to itself, a shared side in both of these. So step 3, segment AD is congruent to itself by the reflexive property. I'm just going to reflexive property. It's reflexive property of congruence, but reflexive property. This is where I can make my triangle congruence statement. Number 4. What do I want to say? Number 4, triangle. I'll call it ABD. Triangle ABD. This guy right here, ABD, is congruent to triangle ACD using angle, side. Oh, you know what? I'm not done with this. I'm sorry. I just wrote perpendicularity. I didn't talk about right angles or congruent. I stepped ahead. So statement 2 is going to lead to statement 4. Okay, my bad. I thought I said they're congruent. Totally did not. So angle ABD, not triangle, but angle ABD is congruent to angle ACD. Ooh, that should be the next statement afterward, because I got to first state that they're right angles. Angle ABD and angle ACD are right angles. This is the stuff that people have trouble with in general. I'm having trouble right now, but it's where people have they're like, what? Like, what do I have to write? Like, where? This is kind of a free constructing your own. This definition of perpendicular lines, right? So the perpendicularity leads to this. And then angle ABD is congruent to angle ACD by definition of right angles. All right angles are congruent. I think it's a right angle theorem, because we did the measures are equal, therefore, that kind of thing. They're 90 degrees, therefore they're equal, that kind of thing. But now I can use, congruent segments, congruent angles, and, the bisector. I didn't even use that one. AD is a bisector of angle BAC. I totally didn't note that either. Statement 1 is going to lead to statement 6, right? So this is going to be a little bit longer. Statement 1 leads to statement 6. My flow of this is terrible. This is why a flowchart proof would probably be nice in a situation like this. Angle BAC is congruent to angle, not BAC, BAD. BAD, the little guy, is congruent to angle CAD by definition of angle bisector. Trying to see my time. Definition of angle bisector. Now I can do my triangle congruence statement. I was way off. Triangle ABD is congruent to triangle ACD. Now by angle side. So I got angle side. See, before I was looking at my diagram and saying, hey, look, I have angle side. Hey, this thing works out. No, yeah, we have to go more based off the information that we have to write this stuff out. We can't just say, look at it. We have to tell them what the information says. And finally, that draws the conclusion that, boom, this segment, BD, is congruent to this segment, CD, which is what we're talking about. BD, I don't know if this is finally. Segment BD is congruent to segment CD by CPCTC, because the triangles are congruent. And then finally, I can then state the length of segment BD is equal to the length of segment CD by definition of congruent. This is also going to be 10 steps. Definition of congruent segments. And then, therefore, D is equidistant to C, to B and C. I don't have a good reason for this. It's probably a definition. Definition of equidistance? I'm going to imagine that that's what, I mean, there is a definition that they're the same distance away. So definition of equidistance. See, it's almost, I'm kind of making up a reason, but I'm not. Like, I don't know if I've ever used that before as a reason, but the concept makes sense. It's based off the previous statement. One statement, literally, once I got to here, one statement led to the next. This led to that kind of thing. Congruent triangles led to congruent segments, led to equal segment lengths, led to equidistance, things like that. So that is 33A. Okay. Let's do 33B. Let's take this other diagram and let's move this one over. Whoopsie. Let's move this one over here. Hope you're okay with that. I'm covering this thing up. Now let's look at part B and do the converse of the theorem. Let me see how much room I have on my computer still. I still have a little bit. I think I should be good to finish this. I hope. So part B, I don't know how much longer the other problems are. I still have 5 more after this. And if they're this long, this is one problem. Converse of the angle bisector theorem. Okay, let's see if I can flow this better without using a flowchart proof. Sorry, I'm going to stick to 2 column. Statements and reasons. Here we go. It might be 10 steps again because of all the things in between. So statements, reasons. Okay. What is given? We're given things based on the drawing, right? So given BD, we can do the... Can I just say that those are congruent? No, I got to do the right angle thing. DB is perpendicular to AB. And DC is perpendicular to AC. Now, I'm going to go right off this given and say what I want to say about it. Right angles. And in this proof, I'm going to go for the right triangle one. I'm going to do the HL thing. So I'm going to say angle ABD and angle ACD are right angles. That's definition of perpendicular lines. Now, to talk about proofs really quickly again, why am I talking about perpendicular lines right here? Because it's based off of this statement. I talked about these being perpendicular. Them being perpendicular is what makes me be able to say what I'm saying about right angles, right? This is the given that you would probably have in that situation. Anyway, so now we have right angles there. And if we have right angles, that means we have right triangles. Triangle ABD and triangle ACD are right triangles because of the previous statement. In triangles, I have right angles. That's definition of right angles. So a lot of definitions here, right? So that's how that's working. Statement 4, I'm going to go with the shared side in between. That's now a hypotenuse to us. Segment AD congruent to itself by the reflexive property. AD congruent to AD by the reflexive property. I completely skipped the other given. I assumed I had already written it, but I did not. Kind of a weird time that I'm writing this other one. Statement 4 should be 5, 5 should be 4. It's okay. It's still a part of things. Segment BD is congruent to segment CD. That's totally given. The only information it's going to lead to is the congruent triangle bit. So I have the congruent hypotenuses here and the congruent legs here. This will give you my HL, and they are right triangles. So my statement 6 will be my triangle congruent statement. Triangle ABD is congruent to triangle ACD by HL. Triangle congruence theorem. We're going to prove that this thing's an angle bisector. So statement 7 is going to be the angles here are congruent. They're corresponding angles in congruent triangles. We're going to use CPCTC for that. So 7, we get to say angle BAD is congruent to angle, that's an angle symbol, angle CAD by CPCTC. If they're congruent, that means AD is a bisector. So 8, this might be the last step. Segment AD is a bisector of angle BAC by definition of angle bisector. I think that's it. I don't think I missed anything there. So it's the only one that wasn't 10 steps. Okay, so that, I believe that's it, and that should work itself out. 8 steps to get that one done. I think because I had less to do to lead into the right triangle stuff, which was pretty nice. Okay, that is number 33. Woo! Very nice. Yes, proofs are a thing. They are real. They do exist, and really, I mean, they work out. Like, it's undeniable at this point, now that I spelled it all out. You see the my work? You're like, yeah, you totally proved something. All right, let's go to number 34. I don't know what this question's going to ask. How do you see it? It's a good question. The figure shows a map of a city. The city is arranged so each block north to south is the same length, and each block east to west is the same length. Okay? Which school is approximately equidistant from both hospitals? Explain your reasoning. So here are the hospitals. Let's say that we drew a segment between these two hospitals. I'm going to draw my best perpendicular bisector to these hospitals as possible. So, for example, my best perpendicular bisector would have been this guy right here. So which school is approximately equidistant from both hospitals? The one that's closest to this perpendicular bisector here. That's Roosevelt School. So Roosevelt School School is approximately equidistant from both hospitals because it is the school that is closest to the perpendicular bisector of the segment that would connect both hospitals at the endpoints, at its endpoints. If that makes sense. Hopefully the drawing made sense. My description describes the drawing. Excuse me. Okay, that's A. That's A. So, A. All right, B. Is the museum approximately equidistant from Wilson School and Roosevelt School? Explain your reasoning. So it was probably another perpendicular bisector thing. So the museum, where's Roosevelt and Wilson? So here's Wilson School, Roosevelt School. Let's draw the apparent perpendicular bisector. If each block is equal distance, then we should probably put it like right there as the midpoint, which means if I draw straight upward, because I can, we can do perpendicularity that way. That's why north-south is pretty nice versus east-west. The museum does not really look like it's near that perpendicular bisector, right? So as the museum does not appear to be up near the perpendicular bisector, at least, the other one just asks what is nearest, kind of, and so that's there. No, the museum does not appear to be approximately equidistant from Wilson School and Roosevelt School because it is not near its perpendicular bisector. In the same kind of perpendicular bisector that would connect both schools at its endpoints and that kind of thing. So that's the thing for part B. All right, that's number 34. 4 questions left. Number 35. Write an equation whose graph consists of all the points in the given quadrants that are equidistant from the x and y axes. 35. Write an equation whose graph... Oh, so these are 3 different parts. I thought that was multiple choice. Yeah. So for part A, to be equidistant from the axes, I guess I have to put up the graph to show you the concept. So to be equidistant from the x and y axes, we're going to have a slope of 1 or a slope of -1, and it needs to go through the origin. So basically, for example, this line right here, it kind of serves as an angle bisector of the two axes. Therefore, it remains equidistant. As you can see, it goes perpendicularly to here and perpendicularly to here, equal distances away. So we're looking at lines that look like that, for example. So in quadrants 1 and 3, and so I just drew it. In quadrants, where'd they go? In quadrants 1 and 3 would be the equation of this line. So for part A, here's quadrant 1, 2, 3, and 4. I'm going to put them down here. A would be the line y equals x. Literally, y equals 1x plus 0 would be that line that would make that thing so. That's how it's going to work. Part B, equations 2 or quadrants 2 and 4. This is now going to be the line that goes over here for the same reasons as we mentioned before, but now it's over on this side. It's the same. It's going through the how do I say it? It's going through the origin, but it has a slope of -1 this time. So this will be y equals -x. Okay. C is a little tricky. C says it needs to go through 1 and 2. Well, it's not going to be a line anymore, at least not a single line. Instead, it will be a V-shaped graph. Now, we did this all the way back in chapter 1, section 1, an absolute value graph like that. That'll keep it equidistant to those two quadrants. That is y equals the absolute value of x. 1 and the absolute value is the h and k are 0, everything like that. Those would be the three answers there, to the best of my knowledge. That looks good. All right, number 36, thought-provoking. The postulates and theorems you have learned represent Euclidean geometry. What'd you call me? In spherical geometry, all points are on the surface of a sphere. A line is a circle on the sphere whose diameter is equal to the diameter of the sphere. I'm going to have to think about this question. In spherical geometry, is it possible for two lines to be perpendicular but not bisect each other? Explain your reasoning. Okay, in spherical geometry, all points are on the surface of a sphere. Okay? A line is a circle on the sphere whose diameter is equal to that. Okay, I think I understand what they said. So imagine a sphere. This is going to be hard to talk about because I can copy and paste a sphere on like Google or something like that. But imagine, this is a circle, but imagine that, I'm going to get some dimensionality to this by doing kind of sphere stuff, like by doing like the dotted line thing. So imagine that, we have a sphere like that, like, oh, that's cool. Like that kind of thing. Like this is like foreground and that's background. This is foreground, that's background. I don't know if that makes sense. But these are good examples of those circles. Okay. So like here's a circle that's like going up and down here, the same diameter as the diameter of the sphere. So that totally works. What are they asking? In spherical geometry, is it possible for two lines to be perpendicular but not bisect each other? So these, I guess these ones, because this is more that vertical circle, it's kind of like, like equator and prime meridian, like for the Earth, right? So they intersect perpendicularly, say like that, okay? Is it possible, and they do over here as well. Is it possible for them to be perpendicular but not bisect each other? Not if the lines need to be the same diameter as the sphere, because these need to be exactly the same. If it was farther off, like over here, that would be fine. But that circle is not the same diameter as the sphere. So I'm going to say no. This is as like equator and prime meridian as, and perpendicular. I'm going to say no. It's not possible. So no, and I don't know if this makes sense to you. I don't know if my drawing helps. I don't have like a ball, which is ironic. I'm a coach, softball coach. No, it is not possible for them to not bisect each other. Now, the bisecting part is another thing we want to talk about here, right? The bisection states that basically this distance is the same as this distance because they intersect, because that's where they end, right? So this distance and this distance are congruent. Basically, these points are exactly opposite each other in that same kind of way as well. For them to be for the lines, so they call them lines or circles. For the lines to be circles of greatest diameter, I'd put that in quotes, of greatest diameter of the spherical diameter, they can't be off center as to manipulate the arc lengths, or segment lengths, and not have them be bisected. The other part of this is they said they have to be perpendicular. So if they're if it was angled, in a certain way, maybe we could have another conversation. Well, I don't know if you could still. They would still be bisectors even if they're angled, I guess. I don't know if they'd intersect at those centers anymore, though. Maybe not. So, yeah, I'm just going to say no. I hope I read that problem right, because I'm moving on. Number 37. We're going to do a proof. 37, 38 are proofs. And we have to do 3 proofs for this question here. All right. Use the information in the diagram to prove that segment AB is congruent to segment CB. AB is congruent to segment CB if and only if points D, E, and B are collinear. See, the interesting part about all this is I was thinking that, we have less problems to do. I was thinking that's one way that this would be like shorter videos and stuff. But also, we wouldn't have any graphs, so they'd be shorter videos. Or for one, we did have some graphs. But you know what stood in the way of not making these shorter? Proofs. Proofs can be very, very long. And especially if they ask you to explain reasoning on other problems that are in a very proof-like manner. Explaining is a proof in and of itself, right? So number 37. So we have this collinearity that they're referring to here, right? We have to kind of, I might even draw this line, at least if not faded to begin with, and just kind of get that concept in play and go like, all right, that line is kind of there. Just keep it in mind. If and only if points D, E, and V are collinear, use the diagram to prove that segment AB is congruent to segment CB. All right, so I assume that drawing should be the first thing that we kind of just say, just by a construction, right? By the way, they didn't say we can't use paragraph proofs, but I think that's just a lot more typing on my end rather than just a good step-by-step process of what's going on. So statements and reasons, let's go at it. I think my statements tend to be longer than my reasons, so I'm going to kind of move this over. So number 1, besides the givens, let me do that construction. So draw DB through E. DB through point E. Kind of stating it's collinear by construction. Oh, I should actually say number 1. Excuse me, D, they said if and only if they're collinear. So D, E, and B are collinear. That's our first given. All right, number 2, we can do that thing by construction. Okay, I think that makes more sense. Okay, so now we've kind of made triangles, right? We've made triangles here and here. I don't know what they want. Okay. I'm going to do an angle. Okay. I'm going to start with these inner triangles right here. And I'm going to talk about how segment DE is congruent to itself using the reflexive property. All right. And then we'll go to, these 2 triangles being congruent, the 2 smaller triangles. Triangle ADE is congruent to triangle CDE by side, side, side. Oh, I'm sorry. I did not mention these other givens. I'm sorry. Let me do that. Give me 1 second. So 2 other givens. I really should lead off with givens. Segment AD congruent to segment CD. I should really mark this on the other one as well. Let's just do this over here. Okay, I drew this. We have it. There's no denying it. It's there. Segment. Okay, we have the reflexive property. Boom. Segment AD congruent to segment CD. That is given. And also segment AE congruent to segment CE. Okay. Now I can do the side one. So triangle ADE is congruent to triangle CDE by side. This is all about CPCTC, right? I'm going to basically hit the angle bisector approach on this. What I'm going to do, I'm going to talk through the rest of it now and then write out the proof. So what I'm going to do here, how much room do I have on my computer? I don't know how much room I have left on my computer. Give me a second. Okay, I have no guarantee that I'm not going to run out of space when I'm talking to you, so we'll figure this out. What I'm going to do here is basically, I'm going to use CPCTC next to talk about these two being congruent. So then we have an angle bisector thing, which, by the way, I don't know if I could have kind of let off with that in some sort of way because we used that proof already. You know, maybe. But now that we prove the triangle's congruent, then we can get to this thing. It's an angle bisector. And on an angle bisector, that means this is equidistant from 2 points on an angle. That these 2 points are equidistant already from there would mean, like, they're not perpendicular, so it doesn't work perfectly, but B is also on that thing, so we just got to prove that these are valid points to refer to when it comes to equidistance. The fact that these points are equidistant as well should imply that. That's the one part that I'm kind of iffy on, if I should mention that these angles are congruent. I don't think I need that, and I don't think I need more congruent triangles, but I need to go more on the fact, oh, never mind. I know what I'm going to do. I got it. Perfect. Okay, I'm not going to do the angle bisector thing. I'm going to use these. but I'm not going to mention angle bisectors, so I got it. I'm going to say angle. So basically, I'm going to prove another 2 sets of triangles congruent now. Angle AD. You know what? I'm going to call it B. I'm going to start talking about the bigger triangle now. Oh, no, I can't yet. I'm doing CPCTC. So I'm going to use angle ADE. It's still the same angle. Angle ADE is now congruent to angle CDE by CPCTC. But now check this out. Now we're looking at the bigger triangle. Now we're looking at this, and this. But here's what we already know about this triangle. We know these are congruent, and we already know these are congruent. You know what we can go to next? And remember, we knew these were congruent by reflexive property, but now we can look at all of DB congruent to itself by reflexive property. Those will give me side, angle, side. So then the triangles are congruent, and then we can use CPCTC to mention those are congruent. I'm using 5 tick marks, baby. So we're going to say now segment DB is congruent to itself by the reflexive property. By the reflexive property. I'm sick of writing. And then there's 2 more statements. Triangle ADB is now congruent to triangle CDB by, I have side angle side now. Side angle side, side angle side. So side angle side. And then lastly, with that, those 2 segments, I'm just going to mark it. Those 2 segments are now congruent to each other by CPCTC. Segment AB congruent segment CB by CPCTC. Everything in geometry is reasoned almost literally by triangles, triangle congruence, and CPCTC. It literally brings through everything that the corresponding parts are congruent. That's what really connects everything within one. It's really cool. Okay, that is number 37. Now, 38 is the last question, but I'm intimidated because we have to do 3 different proofs. I don't know if I can lean one into the next. I really hope that I can, but I'm not sure because this is a 3D object. So Plane P is a perpendicular bisector of segment XZ at point Y. So this thing is being bisected perpendicularly. That means this is congruent to this right there, the segments, from that plane. We're going to have to prove XW is congruent to ZW, point on that part of the perpendicular bisector, because it's a plane that's perpendicular bisecting it. And we can't use perpendicular bisector theorem to prove it because that is using the proof, or the theorem in the proof. You can't do that. And XV is perpendicular to ZV, and angle VXW, where is VXW? Right there is congruent to angle VZW. I don't know if I can do this. Let's see. So part A, I don't know if we can use the same proof for all three. I don't know if I have enough computer room. That's my problem. I don't know if I have enough space. I don't know if this is going to cut off on me and say, sorry, guys, I had to delete stuff on my computer. I don't anticipate these to go this long sometimes. A, XW congruent to ZW. The fact that it's a plane kind of makes it wonky for me, because I got to look at this. XW and ZW. Okay, so we got to look at these two triangles right here, basically. We got to look at this whole thing. My other part of the problem is the given and the fact that I have certain points on the plane. So we're really looking at those two triangles. That's the thing that ultimately matters to me. Okay? So this is for part A. So number one, plane P is perp bist of XZ at Y. I don't know if I need to state other points that are on the plane. I think that can be implied, or I think they imply it. I think that can be inferred because we don't ever mention that on other problems. So I don't need to mention that W is also on this plane with Y. It just happens to be a segment also that we see drawn. So I think that's fine. The fact it's a perpendicular bisector means we have right angles here and here, and that's what I need to write next, right? If it's a perpendicular bisector, the perpendicular part means that angle XYW and angle ZYW are right angles, because that's the definition of perpendicular lines. And then we go to the fact that they are now congruent. Actually, am I going to go right triangle proof, or no? I'm just going to do a side angle side proof. So I'm now going to say that angle XYW is congruent to angle ZYW by definition of right angles. All right, that's drawn. Okay, the next part of the perpendicular bisector is the fact that these are congruent here. Segment XY and segment ZY are congruent to each other. So XY is congruent to ZY. That's the definition of a bisector, or perpendicular bisector, if you will, but definition of segment bisector. The perpendicular part doesn't matter, just the fact that it's a bisector. And then I have, I'm just marking in black here, YW congruent to itself. That is a shared side in both triangles. So segment YW is congruent to itself by the reflexive property. So these two triangles are congruent by side, angle, side. We got side, angle, side in both. Doesn't matter that they're right angles. We just stated that they're congruent, being right angles. So we can say triangle XYW is congruent to triangle ZYW by side, angle, side. And therefore, segment XW, what we're looking for, segment XW, boom, is congruent to segment ZW by CPCTC. XW congruent to ZW by CPCTC. Okay. That is the first one that we covered. That is A. Can't believe they're making you do this. They're making me do this. Part B. What I most enjoy about this is like I'm saying I myself as a teacher, I'm never going to assign problems in the later things, but I would never assign every problem in the thing. So I don't know how many people I even talk to at the very end or who's enticed to listen to this stuff. I might be talking to a very small majority of people, and I wonder if through my analytics I can see how many people actually watch this part of the video. I have no idea. Say hi in the comments if you're at this part. Part B. Statements and reasons for this one. Let's go to what we're looking at next. Completely different part. And listen, here's the problem. Well, here's the blessing. I maybe get to copy and paste some things, and I will if I get the luxury of doing it. XV is congruent to ZV. Here's what I don't like. Literally every part of the proof is the same in this, except I think I'm turning a W into a V. I'm serious. Like, I'm dead serious. I literally believe I'm just turning a W into a V. So, here's what I plan on doing. Hope you don't mind. I'm going to see if this still works by copying and pasting this over. And if anything else needs to change, I will change it. But I believe the only thing that's changing is a W is now a V. So let's see. And the A is now a B. So let's see this. Oops. Okay. Let's change. You know how I change a W to a V? Oh, I can't really do it, but I was going to erase a part of the W. I should probably see where I'm erasing those. But it's easier to do this here. V, V, V. Sorry about this. This is literally probably just the faster way to do this. Let's literally see if this still works. It should, because it's just another part of the diagram, right? Any other W's that you see? You can't talk to me. Okay, let's take a look at this one. Ready? All right. Plane P is perpendicular bisector of segment XZ at Y. That's still the same thing, right? Perfect. Boom. I'm missing a 2. Angle XYV. Here's angle XYV and angle ZYV. They are right angles. Okay. Definition of perpendicular lines. Cool. Angle XYV is congruent to angle ZYV for reasons of right angles. XY is congruent to ZY. This is the bisector portion. That's untouched. Oh, I'm missing a V. YV is congruent to itself. That's this guy now here by the reflexive property. Now I have triangle. Oh, there's a 6 missing. Triangle XYV is congruent to triangle ZYV. So here's XYV and here's ZYV by side angle side. That's the same. And now segment XV is congruent to segment ZV by CPCTC. Yeah, exact same thing. Perfect. All right, I got to copy and paste, and it's the same exact thing. Why they enforce that on you, I don't know. I don't know. Last part is C. Let's see how much I can impart onto here. VXW, that's a whole new triangle. VXW is congruent